All right. All right. Sorry about that. We are ready to go. I have to do a slightly different the right presentation button, a slightly different format. So hopefully this will be all right. We will get going. Welcome back to CS 107. Hopefully you guys have started assignment 0, and I don't think it's too hard at this point. Hopefully it's just about getting used to the Linux system and used to running programs and making programs and cloning repositories and typing on the in the terminal and so forth. So hopefully that hasn't been too bad so far. Okay, today, first things first. So as I mentioned on Monday, the reader is brand new. I wrote it in like 3 weeks over the break, and it was it's obviously got some typos and things in it. People have been telling me about the typos, and I have been fixing them as quickly as possible and then just changing or updating the document on the back end. So please go and re-download the reader unless you want to find the typos that people have already found. So that's it. Have people been finding it useful so far, the reader? Maybe? Okay, good. I hope so. And again, if you do find typos, please let me know, because I want to make it correct. All right, let's see. So it's Friday. Monday is Martin Luther King Day, and there's no class, but I am going to do a video. Unfortunately, the way this course works, we just can't skip a lecture in the big picture. So I'm going to do a screencast of the lecture for Monday. I'm going to have it up by about noon on Monday, I hope, maybe even earlier. Please watch that. It's basically going to be what I would have taught had we all been here and not taking the day away from class. So please do that. Labs start on Tuesday. If you haven't already signed up for lab, please do that. The spots are pretty full. We're actually a little bit oversubscribed for the number of spots. I may have to up the number of spots by a couple for a couple of the labs, only because we have more people than we had originally expected. What that means is that there's only so many computers in that lab, and therefore we're going to have to see what we can do. But I will work it out. But if you are desperately in need of a lab section, you can't find one, email me directly, and we'll try to work something out. All right. The assignment 0 is also due on Monday. Honestly, it should not take that long to do, because on Tuesday, assignment 1 is coming out. So that's our first real assignment. All right. So what are we covering today? Assignment 0, Piazza. There have been a number of questions on Piazza so far, which are great, and that's your first line of defense. If you're like confused about something or you don't know, somebody else might have already asked about it on Piazza. So go there. If you're not enrolled in Piazza yet, email me. I think the link is online, but I can also enroll you, and we should be good to go. All right, and then we're going to cover the rest of this stuff today. Hexadecimal conversions, a bunch of things that are specific to C, some things that are specific to C, data sizes, and numbers, and how do we represent integers in a computer. Okay, that's what we're going to end up with, and then, or we're going to do that for a bit, and then we're going to talk also about Boolean algebra. Okay, so I guess it's going to be in the opposite order. All right, so where did we leave off on Monday? We left off at numbers are represented as binary to the computer. The computer only knows about binary numbers. That's it. And the computer is zeros and ones. That's the bottom line on a computer. The byte is 8 bits of ones and zeros, and everything is byte addressed in C and on your computer. In other words, you can't go and say, give me the third bit in some, like give me the address of the third bit of some value. It doesn't make sense that way. Everything is by bytes. Okay, now the issue is that if ones and zeros are the way the computer understands numbers, and we generally understand numbers in decimal, which isn't the best in terms of translating to ones and zeros, we have to come up with a different way to represent numbers. All right, we do that with base 16, and we use base 16 for a very key reason, which is that it makes turning base 2 binary numbers into base 16 and vice versa very easy. So how do we do that? Well, base 16 is, you will get used to it, by the way. It's not the hardest thing in the world to learn. It just takes a little bit of time to figure out. Because base 16 goes the digits 0 through 9, and then it adds A, B, C, D, E, and F. There's actually 6 more digits involved. Now, why aren't they other like digits? Well, we don't have any other digits in the alphabet or the base 10 number system, so we go with A through F. Okay? Here's how it works out in the computer, okay, or on the translation level. Okay? If we have hex digit 0, that's just 0 in both binary and decimal. And then 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 9 are exactly the same decimal to binary. Okay? And then hex to decimal. With the binary representation, well, we're just counting here. We go 0, 1. This is 2, because once we get past the end of our digits, we have to start over at 1, 0. And then 3, and then 4, etc. Now, when you get to A, in other words, you get to decimal 10, in hexadecimal, you keep counting digits that you have. So you start with A. So A in hexadecimal means 10 in decimal, or means 1010 in binary. Okay? And then B, C, D, E, and F are exactly the same. F means 15 in binary, and that's your top digit. Okay? Anybody got any questions about that so far? You'll see where this becomes relevant in a second. Okay? We write hexadecimal numbers using the 0x prefix, and that's just to designate that it's in hex, right? A lot of times you'll just see letters and go, oh, it must be in hex. But we use the 0x to say if something's in hex. We also use 0b to say if something's in binary, and then sometimes 0d, or just add a d at the end for decimal. Okay? So a number like this, the number that is, let's see, 0x173A4C is a hexadecimal number because it starts with 0x. That's the end of the story there. Okay? And how do you convert that to binary? Well, it turns out it's actually very, very easy. Okay? It's very easy because each hexadecimal digit refers to 4 binary digits. Just like this, whoops, just like the chart we have right here. I've recreated it here, right? What you do is you say, oh, okay, the 1 in hexadecimal, you can easily immediately translate it to 0001. And then the 7 is 0111. And the 3 is 0011, etc. Okay? And A is 1010. And so to convert this to binary, it's a direct, easy translation. No other fancy dividing or like powers of 2 or whatever. You just do the translation by memorizing the digits here. Okay? You should memorize most of these hex to binary conversions. All right? The easiest ones to memorize, I think, are, let's see, did I put it down? Did I put it up here? No, it's maybe on the next, nope, not on the next slide. There's a few, oh, there it is right here. A is 1010, right? It happens to be 10, 10, 10. That's an easy one to remember, right? C is 1100, right? And that's actually 12. And then F is all ones. Okay? If you memorize those, then the other ones are like 1 away from those ones. So it's actually pretty easy to do. But again, the translation, very straightforward. Okay? And what it also means is that if 8 bits are a byte, how many hex digits does it take to make a byte? If there are 4 bits in each hexadecimal, how many hex digits does it take to make a byte? 2. So that's easy too. So if we want to represent a byte, it makes it very easy. And we already said that bytes are the representation of the addressing and so forth that we use. So this is why we use hexadecimal. Okay? Let's do a conversion the other direction. If you're converting from a binary number to hex, you have to start at the right-hand side. Okay? And you peel off the first 4 binary digits. So 0011. And you go, oh, okay, 0011 is just 3 in hexadecimal. So that means the last digit is going to be 3. Then you go to the next one and you go 1101, right? And that's a B. And you've hopefully memorized maybe that A is 1010, and so you go, B is 1011. And you go, okay, that's a B. And then you keep going backwards one at a time until the last one, which might or might not have 4 digits in it. It will have, the last one will either have 1 to 4 digits. And you just take a look at the last one, you go, oh, it's 11, which is the same as 0011, which is, again, 3. Okay? The conversion is not that hard. You will get used to it as we go along. Okay? Oh, there we go. I'm just kind of showing you how it goes through. All right? Nothing too horrible, I hope, so far about that. If you do want to convert from decimal to hexadecimal, now it gets a little bit trickier. What you have to do is you have to actually say, okay, now I'm converting a decimal number into powers of 16. And so you have to divide by 16 and take the remainder. And that remainder ends up as the last digit. And then you divide what was the original quotient by 16, and the remainder is the next digit. Okay, you can see it up here. We are never going to ask you to do this conversion in real life, like by hand. You should kind of understand how it works, but we're never going to ask you to do that. Okay? Hexadecimal to decimal is actually a little bit easier, I think. Hexadecimal to decimal, you just go, okay, you take each letter or each digit in the hex thing and you multiply by its associated power of 16. Okay? So you've got 7 times 16 raised to the 2 plus a, which is 10, 10 times 16 raised to the 1, plus f, which is 15 times 16 raised to the 0. Think of it just like doing a decimal expansion like that, and you can figure it out. Now, the reason I'm flying through these is because, again, I'm not going to ask you to do any of this, and nobody's ever going to ask you to do this because computers do it very easily. And if you want to go do some conversions, write a one-liner in Python, or just go to a website and do convert from hex to decimal. Okay, it's that easy to do. So you're going to have to understand how to do conversions from binary to hex and hex to binary. Those are the big ones. And you're probably also going to need to know how to do decimal to binary and so forth. But the hex to decimal, decimal to hex, just do it on the computer. We're not going to make you do it by hand. Okay? All right. So there's you can also do this. You can do the conversions from binary too, by the way. bin and then the number in hex notation will give you the binary equivalent. So you can do these conversions pretty easily without having to sit down and figure it out. But you should get fast enough so that you can figure it out. Why? Because you'll see it all the time, and it's worth your time to memorize this stuff, okay, or to figure out how to do it. Okay, let's step away from the numbers for 1 minute. And this came up in class the other day, and then a couple questions on Piazza. What are these strange arguments to main? Okay, if you've already done assignment 0, you've kind of had to figure some of this out. But what they are the command line arguments. So if I go to let's see, nope, this will do. If I go to a page, let's make it big enough so people can see it, and let me log on to Myth. There we go. And there we go. OK. As you type a command in Linux, if I type ls and then *.c, that says give me all the files that end with .c, right? These are the command line arguments. The command line arguments are ls and then *.c. There's actually 2 of them. The program name is one of the arguments, as it turns out. OK, so if I do that, and then let's see what I've got 3 files in there, and that's how you represent arguments. Now, I could say ls a, b, c, d, e, f, g, and this now has how many arguments? This has 1 for the ls, 2, 3, 4, 5, 6 for that. Make sense? That's how the arguments work. You can do interesting things with arguments. You can put them in quotations. If you say A, B, C, and then D, E, F, each part in the double quotations means a separate argument. So you can do that. But we will use arguments often in CS107 instead of having you type things in. Like you're not going to have a user type things in a lot of times. A lot of times you're just going to have the command line arguments tell the program what to do, just like we do with the ls command or any of the other commands. Okay? Anyone know what the most important command you should get to know in Linux is so far? Not GCC, although good answer. Man, yes. Man is the name of commands that gives you the manual, right? So if you want to know how to use the ls command, you can type man space ls, and it will tell you all of the options that you have with ls. Okay, and if you do this, by the way, you type Q to quit out of this, and the arrow keys or the vim command keys will get you up and down. But there's a zillion options for these sorts of things. So you will do that, right? One of the things that we're going to talk in depth about in a couple weeks is the string library And let's see if this, yeah, man string will give you all the different functions from the string library. You will get very used to doing this, but it's a super important command because it gives you the help right there in the terminal. Okay? All right, so back to, oh no, they're going to give me the, oh no, did it die? Hang on. It looks like it died. Hold on. Open, let me open this from my local. Might have been a problem with that. Hang on a sec. Weird computer issues today. I don't know what happened with that, but that's the way it goes. Lecture 02, open that one. And we will try to find where we were, which was down here. There we go. OK. Window and view, maybe slideshow. There we go. OK. OK, so those are the command arguments. Remember, the first argument is the name of the program, which is most of the time not one you really care about. OK, so, whoops, you know what? It's going to, there we go. OK, so these are the command line arguments. The actual arguments themselves, we all know what ints are, right? They're just numbers, integer numbers, right? This thing is interesting. It actually means an array of strings. Okay, you'll sometimes see it like this, okay, where it says char star argv bracket bracket. Basically means you're going to have a set of pointers in an array that each point to a different string. That's what that actually means. Okay? All right, what can we actually do with this? We can actually go and write a program like this, which says, go through all the arguments, go from 0 up to the number of arguments, because that's what argc is. It's the count of how many arguments you have. And then print out the argument number and then the actual string that goes along with that. I think I have it up here, yeah. This is what it actually looks like when you print it out. Okay, hold on, I wish that little, there it goes. Okay, so this is what happens when you actually run this program. So if you say, you make this program, and you say /argv underscore argc, and then you say this is a sentence. Well, we know that there's 1, 2, 3, 4, 5 arguments. And when we go through this loop, we go from 0 to the number of, less than the number of arguments, 0, 1, 2, 3, 4. The 0th argument is the program name, and then 1, 2, 3, 4 are the various parts. Okay? So you'll see that. And you'll many times ignore that first argument. Okay? If I wanted to ignore the first argument here, I would go from 1 up to argc. Easy enough. Okay? All right. Questions on that? argc and argv? We're going to use it all quarter, so start to get used to it here. Okay? It's the same exact thing there. Okay? More details on argv and argc. You will understand this diagram a little bit more in a couple weeks. But what it really means is argv, this form here means argv is a pointer, and it is a pointer to a bunch of other pointers. That's really what it means. Okay? And each one of those pointers, let's say that argv had a value of 0xa0. That's the address of the first pointer. Okay? And that pointer, it has a value of, let's say, 0x10, and that means that it points to this cats here. If I typed cats as the argument after the, actually in this case that would have to be the name of the program, I guess. But then the next one over in the array is 0xa8, and it is points to a different string. Okay, a couple things to notice from there, or at least one big thing to notice from this. What is A0 plus, or what is A8 minus A0? Yeah, 8. If you don't get the fact that it's like if the hex scared, you don't worry about it too much. But that's basically saying A8 minus A0 is 8, meaning that this pointer in here is how big? 8 bytes, as it turns out. Turns out on our myth machines, pointers are actually 8 bytes long. So, as it turns out, each one of, like this argv will point to the first pointer. The next pointer is 8 away, and then 8 away, and then 8 away. And if you say, let me go back up here again. If you say argv bracket some number, it knows which one of those to go to. So a couple things to take away from that are, that you can use this bracket notation to walk through arrays, just like every other language you've used so far, which is great. And the second thing is that somehow under the hood, the compiler knows how to count by 8 when you say go 0, 1, 2, 3, 4. It knows that it needs to count by 8 to get to the next one. That's the kind of level we're going to be ending up at in this class. Thinking about, oh, okay, what's actually happening here? Oh, we've got an array of pointers. Each pointer is 8 away from the next one in an array because they're pointers. And the compiler somehow needs to know how to count by 8. Notice there's no 8 in this whole program up here, right? The compiler needs to know that, as it turns out. OK, so that's a little side note for later. You will sometimes, in fact often, see the char star argv bracket bracket recall, like instead looking like this, char star star argv. Turns out it's identical. When you're in a function, calling it in a function, that's exactly the same format. It means a pointer to an array of pointers. That's what char star star means. Okay? All right, so we'll see these details later, but I figured I'd at least introduce them right now. Okay. All right. Let's talk about data sizes. I kind of just mentioned data size in a roundabout way a second ago. Let's actually think about how C represents data. Okay? In all the programming languages you've done so far, if you've done the CS106 series, you will have seen numbers like ints and doubles and maybe longs, which are ints that hold more bits. You may or may not have seen shorts. You probably would have seen chars, okay? And you may or may not have seen any of the unsigned ones, okay? Here's how this works. You have a declaration over here of, if you just say char, what that means is it is a signed character. In other words, the character can be either negative or positive. Why they ever allowed characters to be negative, I still don't know, but that's the way it goes. And if you say short, right, that means that it is a signed short. Or if you say int, it means it's a signed int. We leave off the sign. You can say signed if you want to, but if you leave it off, it just means we're dealing with signed integers. Okay? If you have unsigned, if you say unsigned before it, it means it can only be positive. Okay. The interesting thing about it here is that the number of bytes associated with each type, A, can be different for different computers, which also always struck me as a little bit weird, but it's the way C was invented. When C was invented, many of the computers had different sizes for the underlying character or underlying integers for the type, for the size of the addressing and so forth. So they just said, well, some of these don't need to be different sizes. Chars are always 1 byte on both. By the way, we're in this land now. We have made it to 64-bit land. That's what the MITH computers are all built in. Okay, they're 64-bit computers. And so this is the column we really care about. Chars, 1 byte. In other words, it takes 8 bits to hold a char, and that's all you get. 0 through 255, or, as it turns out, negative 128 through 127. We'll get to where that 128 part comes in a little bit. Ints. Ints are another one you want to know by kind of right off the top of your head. Ints are 4 bytes long. Okay, that's 4 bytes. How many bits is 4 bytes? 32. Each byte is 8 bits, so 4 times 8 is 32. That's how many bits an int is. Okay, we'll get into more details about that later. The other ones that are interesting, longs on 32-bit machines, they were only 4. Now they're 8. So don't worry about the 4 part. Just know that they're 8 bytes long. These other two are interesting here. These are defined by the standard. Okay? There's one more that's missing there that I should put up too. There's one that is called size underscore t, and that is one that is also an unsigned 64-bit number on the MITH machines, as it turns out. Okay? It's just another integer. You'll see that in some of the assignments, and you'll start getting used to that. Okay, but what it means is, so an int64t is defined as a 64-bit integer, either signed or unsigned. All right. Pointers. All pointers, as it turns out, on our machines are 8 bytes long. Okay? All pointers are 8 bytes long. That's going to become important later when we think about how are we manipulating pointers. Okay? Anyway, that's how C does it. Question?
Kind of related to this, if you go back 2 slides, why do at the bottom, cats and dogs, why do one slide include by 8 and the other?
Yeah, this is such a good question. The question was, for people who didn't hear it, up here in this array, it goes A0, A8, that's 8 away, and then B0 happens to be 8 away from A8. If you think about how you add the digits, that works out. And then those are by 8. But then down here, they're by 1. C, A, T, S, 0, 1, or 10, 11, 12, 13, 14. OK. Does anybody know why that's the case in here? Yeah. Because they're characters. And what did we say on that other slide? Characters are each 1 byte each. So when you're talking about a character string, each one is 1 byte here. When you're talking about an array of pointers, each one has to be 8 away from each other.
No, I mean, the question is, if you're comparing the 2 slides, slide before.
Oh, did I have them wrong? Oh, oh, sorry. I didn't mean to insult your intelligence. Yes, this one's wrong. That one's wrong. You know what? I changed it. This came up. I looked at it and changed it earlier. This one's the correct one. Yeah, sorry about the mistake. I'll fix it for the slides. OK, any other questions on this? OK, so those are the number sizes that we're going to deal with when we talk about C, and then when we go a little more under the hood and we talk about assembly language, we'll talk about numbers in those formats. Notice they're always powers of 2, 1, 2, 4, 8. That's going to become important. You don't have a byte size of weird numbers that aren't powers of 2. OK? All right, so we talked about the guarantees. The only ones that are really guaranteed are char, int32t, and int64t. I don't care that you know any of the 32-bit ones. It doesn't matter. The point is that sometimes they're different, and you should know these ones kind of by heart. Okay, you'll get those in your brain pretty quickly. Okay, like I said, we have these unsigned versions, which means there's no negatives allowed. By default, just a signed number. All right. You can write these many different ways, as it turns out. You can say unsigned long, which means the same as unsigned long int, which means the same as long unsigned, which means the same as long unsigned int. Oh, so confusing. Normally, we leave off the int if there's something else there, and normally we put them in, normally we would just say unsigned long. All right, they have to be the same as long unsigned. You'll see it in kind of different ways, but you'll kind of standardize on 1 or 2. Okay? All right. Now, here's where things get a little bit interesting. As I kind of said, pointers are 64 bits long. Okay? The computer can actually address up to 2 to the 64 bytes of memory, meaning that your computer can address a lot of memory. 2 to the 64 is actually 16 exabytes of memory. I don't even know where exa falls in the like giga, et cetera, mega, giga, et cetera. It's like 2 or 3 up. Peta, exa, I think it goes, something like that. Okay? It's a lot of memory. Okay? Older machines could only address up to 4 gigabytes of memory. So if you bought a machine about 10 years ago, you probably could never install more than 4 gigabytes, did I say megabytes? Gigabytes of memory on that machine. Why? Because it only had the ability to hold pointers that were 32 bits long. Now we've got pointers that are 64 bits long for our machines, and we can hold lots and lots more memory. Okay? And that's so much memory that 2 things about that. A, we probably won't have to go to 128-bit machines for a very, very, very long time if we care about addressing. It's just not even going to be necessary for a very long time. And the second thing is that, that Linux actually limits this even further because it doesn't need all that either. Linux actually says you can actually only get up to 2 to the 48 bits, as it turns out. Not that important right now. Okay, not that important. Point is that we have pointers that are big and can hold lots of different addresses. Okay. Now, here's where things get a little bit interesting. Pointers and memory address pointers can point to a particular byte. Okay, so we had a picture before where we had, I'll do it up here. We had argv, which pointed to here, and then this was another pointer which pointed down to some, cats sort of thing here. Okay? And those pointers can point to a particular address. I'll actually make it more specific. That one points right there. Okay? But the one question is, how do we actually store the individual bytes in memory? It's interesting. We actually have choices for this. Take a look at this. If you look at a 4-bit or a 4-byte hexadecimal number, okay? So if you look at this number like 0, 1, 2, 3, 4, 5, 6, 7, 0x that. That's a 4-byte hexadecimal number, right? 1, 2, 3, 4. We can separate out all those bytes, right? Here's the first byte, here's the second byte, here's the third byte, here's the fourth byte. If you're looking at how that's stored in memory, we actually have different ways of storing those. Okay? What we can do is we can either store the bytes in what we call big endian order or little endian order. Okay, what does that mean? Take a look at this number here. This is a 32-bit, that's the same number in binary. I've converted the binary already. Okay? And if you look at the bits in it, the most significant bit, that's the one that means the most to the number, is actually this bit way over here. It happens to be 0. The least significant bit is the one all the way over here on the right, which is the one way over there. Why is it least significant over here? Because it doesn't count as much to the number. If you think of any numbers, right, the digits higher up, if you say 456, the 4 means more to the number than the 6. Okay? If you look at these in bit order, you might think, okay, I'm just going to put the bits in memory in that order. Well, we don't actually do that all the time. As it turns out, what we do is we take these byte chunks and we store them in an order which can be either this byte, then this byte, then this byte, then this byte. Okay, that means that in memory, here, we'll draw out a memory picture here to actually make it a little more specific for you. If I said that, let's actually redo this like this, and let's say that there's an 8-byte number here. No, we'll make it let's see. We'll make it a 4-byte number like this one. Okay? If we said that this was byte 01, and this was byte 02, and this was byte 03, and this was byte 04, we could store that number 0, 1, 2, 3, 4, 5, 6, 7. We could store the 01 here, the 2, 3 here, the 4, 5 here, or the 6, 7 here. That's one way to do it. The 1 is the least one in memory, right? The 01 happens to be at 01 in memory. The 2, 3 happens to be at 02, which is higher in memory than the 03, than the 04. Does that make sense? Kind of. People look at me like I'm a little crazy. We could also store this like this, as it turns out. If this was 01, 02, 03, and 04, we could actually store it in what we call least significant, or we call it little endian order. In other words, we put the little end of the number first. Which of those 4 bytes is the littlest, the one that's least significant of the 4 bytes? 0, 1, 2, 3, 4, 5, or 6, 7? 6, 7. What we do is we put the 6, 7 here, and then the next byte in memory we put the 4, 5, and the next byte in memory we put the 2, 3, and the next byte in memory we put the 0, 1. And you think to yourself, why would they ever do this? Well, it was a choice somebody had to make, okay? And they said, we want the most significant part of the number to be highest in memory for some reason. And they made that choice. Well, what does that actually mean for us? There's the diagram I just tried to draw down there for you. Okay? We have 2 different ways of storing this. Most of the time, this will not matter to you at all, as it turns out. It's going to matter when we get to assembly language later, when we have to look at individual bytes in memory. But for most of the time, it's not going to matter. You just should know that it exists. The MITH machines and all of x86 machines, the Intel machines, are all in this little endian format. Okay? This is the way it's stored on your machine. Okay? So that's all there is to that. But most of the time, we're not going to care. I just needed to show you that so that later, when it becomes necessary, you'll go, oh, I think I remember that, and you'll go relearn it as it goes. Okay? All right, so here's what it looks like on our memory. That's the same exact thing. There we go. If we have a program like this, okay, let's say we have a program like this where we say, okay, int a equals 0x 1, 2, 3, 4, 5, 6, 7. By the way, you can say that. You can put the 0x there, like that. If we just print it using the %x, I've got some formatting in here, so it puts the 0 first. If we put the %x in there, it will print out in regular old number format. So if we say, here's our number, 0, 1, 2, 3, 4, 5, 6, 7, it will actually print out in that format. Okay? Let's see if I can actually run this for you. Let me actually do this again. I will try to not screw up the thing. There we go. Okay. Let's see. CS107. By the way, all the lecture slides are going to, or all the lecture code will normally be posted, not there, samples, lecture 2. Okay, so all the code will be put right in a lecture. So you can go check it yourself. Okay, so we have let's look at the big endian. If we look at the big endian.c, this is the program we just had up there. All it's going to do is take the number and print it out to the screen. Okay, so if I make it, I think it's already been made, but we'll see. Make big endian, it says it's up to date. If I type big endian, it says 0x 1, 2, 3, 4, 5, 6, 7. Okay, that's the way the number gets printed out. What I want to do is I want to jump into GDB for a second. This is the debugger that we've been talking about. Okay, if we go into GDB and we actually say break on main, that will say run the program until the beginning of the program. A little weird. And if I say run it, it will actually run to the first line and not quite do this line yet. It hasn't actually run this line. Okay. But if I say next, it will actually do that. So at this point, what it's done is it's put 0x 1, 2, 3, 4, 5, 6, 7 into memory somewhere. Okay. If I print that number, and by the way, in GDB, you can say p/x to say print in hexadecimal, a, that gives us the number like we think of it normally. Okay? And it left off the 0 because it doesn't worry about the leading zeros in that case. Okay? We can also print out the actual memory of where that is. If I say x, that prints out the memory, x slash, in this case, 16, because I want 16 bytes, and like that. If I print out the memory, how do I get the memory address of a variable in C? Remember this? Yeah, ampersand a will give me the memory address of a variable. You can do that for any variable in C. Okay? Ampersand a will do that. Take a look at how the memory is laid out. Here's what this means. This means that there's the address, by the way. It's some really high address in memory, as it turns out. And the first byte is 6, 7. The second byte is 4, 5. The third byte is 2, 3. And the fourth byte is 0, 1. Little endian format. Okay? That's what's happening with the numbers when they get stored in memory. Again, I don't expect you to know how to do this in GDB yet, but you will quickly learn how to use GDB. Okay? All right. Any questions on little endian or big endian at this point? What I think is yeah, question. Yeah, that's a good question. So let me go back here to there. If you look at a number, okay, here's the number, 0, 1, 2, 3, 4, 5, 6, 7. The least significant part of the number is the end part. Why? Because if I type 400, if I do 456, the 6 doesn't mean as much as the 4. Right? So that's what it means up here like this. It means that the 0, 1, 2, 3, 4, 5, 6, 7, if that's our number, the 6, 7 doesn't mean as much as 0, 1. Okay. We don't, and this actually confuses people at first. They think, wait, we don't put all the bits backwards when we're doing little endian. We put the bytes backwards. So we take the 0, 1, the 2, 3, the 4, 5, the 6, 7. We say, which one's the least significant? The 6, 7. Which one's the next least significant? The 4, 5. Then the 2, 3. Then the 0, 1 is the most significant one. And that's how we end up putting them in memory, as it turns out. OK, again, you will not need to get, you'll see this now, and then we'll come back to it in a few weeks, and you'll go, ah, now I see why it's important. OK, answer your question? OK. All right, so that was the thing. OK, tell you what, let's take a 3-minute break. I'm going to, yeah, after I get a question. Question? When we were doing which? Oh, the second line is the farther down in memory. It's not part of our program, as it turns out. Yeah, so this part is not there. Any other questions quickly before we go to? OK, we're going to take a 3-minute break. I'll always try to have some break in the middle here, so you can, if you want to come up and ask me a quick question or whatever, you can. But these are long classes. I get it. All right, let's come back from our little break. Any other questions right now before we get going into back into these things? Logistical or otherwise? OK, let's get going into Boolean algebra. So this next part may take you back to some Boolean algebra you might have done in high school or even grade school or whatever. I'm not sure where everybody does these things now. Or if you're in any electrical engineering classes, you do a lot with Boolean algebra. Okay? We need to deal with Boolean algebra because we are going to be dealing with bits themselves, and we're going to be dealing with how we manipulate those, and Boolean algebra is the way we do that. Okay? What do I mean by Boolean algebra? Well, you've seen these before. You've seen some of these things kind of before. You've done Boolean algebra. You've done Boolean logic with logical and or and not and that sort of thing, right, for true-false values. We're going to go one level deeper and deal with the individual bits for our Boolean algebra. So what do we have? We have 4 main Boolean algebra functions that we're going to care about. We have the not function, we have the and function, we have the or function, and we have what we call the exclusive or function. Okay? You've probably seen these in other math classes or whatever, so that's good news in that case, hopefully anyway. Okay? And let's see if I can get that little thing out of there again. I don't know how to do that. But what we're going to do is we're going to talk about these 4 operations, and they're logically pretty simple, right? Here's the truth tables for them. If you have a 0 and you apply the not operator, you get a 1. If you have a 1, you get a 0. That's the only one that only takes 1 operand. The other 2, and you need 2 things that you're anding together. And if for each bit, if the bit in A is 0 and the bit in B is 0, A and B is also 0, right? Same thing for 0 and 1, 1 and 0. And if they're both 1, that means that the answer is 1. It's an and thing. Both A and B are 1, therefore the result is 1. OK, that should not be too confusing to you. Or is the opposite in some ways, right? Or says if one or the other is true, then the answer is true, the result is true. OK, so 0, 0, neither one, so the answer is 0. 0, 1, 1, 0, and 1, 1 are all have one or both, in this case, true, so the answer is 1. So that's the truth table for or. And then there's this exclusive or, which might be a new one, so not everybody studies that. But exclusive or just says, it's basically saying if one of them is true and only one of them, then you have the result being true. So in this case, we have A and B both being 0, so neither one is 1, so that's going to be a 0. We have 0 and 1 for A and B, and that's a 1. We have 1 and 0, and that's also a 1 because one of them was. But when we get to 1, 1, they both are 1, and so exclusive or says, oh, if they're both 1, the answer is actually 0. Okay, that's how exclusive or works. All right, so hopefully that's not too, most of that is not new in the big picture. What might be new is when we're talking about applying them in what we call a bitwise manner. You know how in C and Java you have ampersand, ampersand? Did you ever wonder why it's 2 ampersands? Yeah, the reason is because those are for the logical operations, which say take the entire number and the entire other number, and if one's true and the other is false, and you're doing and, then the answer is false. In this case, we have a single ampersand, which means take each bit at a time and compare each bit and flip the bits and set the bits in the result accordingly. So let me give you an example. If you have 0, 1, 1, 0, and you're doing AND with 1, 1, 0, 0, you take each bit at the time and you go, okay, 0 and 1, nope, it's not, they're not the same, so the answer is 0 for that bit. 1 and 1, oh, they're both the same, so that's going to be a 1. 1 and 0, nope, not the same, so it's going to be 0, or not both ones. And 0 and 0, also not both ones, so 0. Bitwise now. So what that means is this is going to be the way we are going to individually target particular bits in a number. Okay, remember I said that we can't really do that in the big picture. We've got like these 8-bit chunks. This is how we're going to do the bits individually. Okay, all right. Questions on that? Yes. If they're both the same, you can take a look at the one up here. Do you see anything that we might be able to do something similar to that? Like, not exclusive OR. That would say if they're the same, right? Yeah. Good. All right. So like I said, be careful. You'll see the different symbols. We use the exclamation point for logical not. We use 2 ampersands for logical and we use 2 ORs for logical OR. There isn't actually a logical exclusive OR, as it turns out. But now we're talking about the bitwise ones, so you're only going to use a single one. The compiler will often give you a warning if you use the 1 instead of the 2 and it thinks you need a 1, but it doesn't always do that. So don't be surprised when you're doing like assignment 1. If you put 2 ampersands and forget about the fact that it's bitwise you're dealing with, you get the wrong answer and you go, I have no idea what's going on. Just go back and think about that. Okay? All right, there's some more examples here. If we say, let's look at exclusive OR, 0, 1, 1, 0, exclusive OR with 1, 1, 0, 0. 0 and 1, yep, one of them is, so the result in that bit is 1. 1 and 1, they both are, so it's a 0. 1 and 0 is 1, and 0 and 0 is 0. Okay? Hopefully that's not too bad either. All right, let's look at a mystery function. Here's a function for you. Okay? And this is the part that I care about. This is just main how to actually print it out. What we're going to do is we're going to set 2 variables to be what? The first actual argument and the second actual argument. It's nice. We're going to use a function called ATOI. If you don't know what that function is, where are you going to look to figure out where it is? Man page, man, ATOI. And it says, oh, ATOI converts a string to an integer. Right? And you say, oh, look, it takes a string and an integer, and it says, well, okay, so it takes a constant char pointer. That means a string that you can't change. That's what that means. Okay? And then it's going to return to you the integer, or it's going to return to you the long if you're going to do ATOL, etc. And if you go down here and you keep going, you'll see it tells you the return value, and the return value in this case is the converted value. Okay? So that's how that works. Okay, so we're going to do that, and we are going to look at the function. So take a minute. Tell you what, take a minute. Talk to your neighbor. Oops. No, no, no. This is what happens when you're using the wrong thing. Did everybody see it? Did everybody see it? Okay, don't take a minute. Think about what you just saw. So what this is actually doing is we're doing this. We're saying, look, if x is not equal to y, it's interesting. We're passing in a pointer to x and a pointer to y. And we're saying if x is not equal to y, we're going to apply this weird thing. We're going to say y equals, the value at y equals the value at x exclusive ORed with the value at y. And we're going to set that into the value at y. Then we're going to take the value at x and we're going to do the exact same thing again. We're going to say x now equals the value at x exclusive ORed with the value at y. And then we're going to do the same thing again. We're going to say y now equals exclusive is going to be x exclusive of y. And you say, what is going on here? As it turns out, this is doing a swap function. It's swapping the values without a temporary variable. So if I had asked you to, say, do a swap function, and I said you can only use the variables that you pass in, you can use no other variables, you might have gone, I don't know how to do that. How do I swap something without doing that? What this relies on, and this is just a neat little trick, by the way, what this relies on is the fact that x exclusive ORed with itself is 0. Because a number exclusive ORed with itself has to be 0, because if you had 0, 1, 1, 0, aren't they all the same? So it's going to have to be 0, 0, 0, 0. In fact, that's a really fast way of turning a number into 0, as it turns out, is exclusive ORing it with itself. But that's really what it's doing. So this is actually a really neat function here. Yeah, Davis. Why do you need the asterisks in this case? Yeah, so this is where reading the C primer is going to help and remembering some of the things we learned in 106B, as it turns out. This means if you're passing in a pointer, you have to dereference that pointer to get to the actual value. Okay? So if in the function we have x and we have y in the function, those two are not the numbers we're passing in. It's not like 4 and 5 and we're swapping 4 and 5. That's a pointer to somewhere else in memory that has a 4, and this is somewhere else in memory that has a 5, and that's how that works. So if you want to get to the value 4, you have to do asterisk x, which dereferences it. Okay, same thing for there. All right. Anyway, take a look at this in a little more detail. Go try it out, and I've got the code online if you want to try it out. Okay. All right. You have a question? No. Okay. So we can actually represent numbers as their respective bits and think of it as what we call a bit vector. What does that mean? Well, a bit vector is simply the number in binary form, and we think about it as being a series of zeros and ones like a vector or like an array, right? It's not, it's just a number, but we can think of it that way. Okay, so let's say we had a bit vector A, which was 0, 1, 1, 0, 1, 0, 0, 1. Doesn't that look like an array of zeros and ones? That's what it looks like. It's not at all, as it turns out, but that's how we can think of it. Okay? And then what we do is we say, okay, this is the 0th bit. And then 1, 2, 3, 4, 5, 6, 7. This is the 7th bit. And that's how we think of the array like that. Again, it's not an array. You just have to kind of abstractly think of it that way. And then we have bit vector B, 0, 1, 0, 1, 0, 1, 0, 1. And we can say that those represent the ones are their respective bit numbers, right? So this one, okay, 1, that's at the 0th bit, right? So that's going to be that's going to be like the 0th bit is on. Nothing at the first, nothing at the second. The third one is a 1, so that's the 3 over here. Nothing at the fourth. The fifth and the sixth are both 1, so our bit vector is 0, 3, 5, 6. Take a minute and think about that. All we're saying is take this bit and just consider them as if it's a 1, it means that number for the bit number is represented. So the 1 there is the 0th one, so this set has a 0 in it. And it's because it's a 1. The 2 does not have a 0, so there's no 2 over here. That's all that means. For B, it's the same sort of thing. Now, as it turns out, if you use these Boolean algebra operations, you can actually do a little set arithmetic on this. So the OR is a union of those. And that hopefully makes sense that you're getting all of them from both of them. Because if you do A or B, you go, OK, 0, 0, nope, nothing there. Yep, there's 1 in the second one. There's going to be 1 in the third because of this one. There's going to be 1 in the fourth, the next one, because I read it backwards. In the next one because of that one. 0, 1, oops, I got out, yeah, 1, 0, 1. So that's what's going to come out there. It's the union of them. All the ones that were in both of them are now in the final one. And gives you the intersection, right? Only the ones that are in both. So if we intersect A and B, if this is a set of A and this is a set of B, the only ones that are in both are 0 and 6. So when we do A and B, we get the 0th bit and the 6th bit. Good? We won't see this too much. You just kind of got to know that sometimes you'll see the bit vectors associated with your programs. Okay? All right. This one's a big one. Bit masking. What we can do, because we can't individually get to a particular bit, sometimes we want to get to a particular bit, or sometimes we want to take away particular bits from a number, and we want to just leave the bits we care about. Okay? What we can do is we can apply the Boolean algebra to what we call mask off those bits. So in other words, if we have, let's use this as an example here, and let's put another one, 1, 1, 0, 1, like that. Okay? If we want, what if we only cared about those 4 bits of the number? We want to maybe get those 4 bits alone and get rid of these bits. Okay? If we're going to get rid of these bits, what's the operation that will, what numbers can we put here and do an operation on it that will always end up with 0, 0, 0, 0 down here? And if we did and then what number here? 0, 0, 0, 0, the answer for all those would be there, right? But if we wanted to do and for the whole thing, what would we have to make these ones so that it becomes 0, 1, 1, 0 down here? What would we have to make the 4 bits here if we anded it? Right? We'd have to make it all 1s. So if we do a number anded with 1, 1, 1, 1, 0, 0, 0, 0, doesn't that mask off, in other words, give us only these bits? Turns out it does. Okay, so that's actually kind of a neat thing you can do with these. Let me show you some examples. You're going to practice lots of these examples in lab next week. Okay? The example of this one is, in this case, if we do 0x, 8, 9, a, b, c, d, e, f, and we and that with ff. Okay, what is ff if we have all 8 or all 4 bytes of that? 0, 0, 0, 0, 0, 0, ff. Right? And that's all zeros, all zeros, all zeros, all zeros, all zeros, all ones, all ones. And if we do that and we and it with 8, 9, a, b, c, d, e, f, 8, 9, a, b, c, d, e, f, okay, all ones means that that f is going to remain, because anything anded with all ones remains. Anything anded with all ones remains. The e remains. What's anything anded with all zeros? 0. 0, 0, 0, 0, 0. Okay? So does that make sense how we masked off that one byte? We actually took this and we said, fine, if we only care about the last 2 digits of that number, we need to and that number with 0xff, and that gets rid of all the top ones, all the 8, 9, a, b, c, d, e, f, or 8, 9, a, b, c, d, and it leaves ef. Are we good there with that one? Let's look at some more examples. Okay, by the way, one useful expression is if you do not 0, well, that takes the zeros for however big your number is and makes them all into 1s. That's how you get a number with all 1s in it. Not 0 gives you a number with all 1s in it. Okay? You'll do lots of that for assignment 0 or assignment 1 and the lab as well. Okay, so here's a challenge for you. Write an expression that sets the least significant byte to all 1s and all other bytes of the number unchanged. Okay? I guess it's not a challenge because my slide thing is wrong, so not a challenge. You can see it up here. Here's how we might do it. All right? If we want to do 8, 7, 6, 5, 4, 3, 2, 1, and we want to just change that 2, 1 into ff, if we do j, let's say that was j ORed with 0xff, doesn't anything ORed with 1 become a 1? So that means that the byte here, or the byte here, ORed with all 1s, leaves all 1s, and we already said that f is all 1s. I'm seeing a little maybe confusion. No? If you are, that's okay. This stuff takes a little time to get in your brain. Here's another one. Write an expression that complements all but the least significant byte. What does complement mean? It means flip all the different bits, right? So we basically want 8, 7, 6, 5, 4, 3, 2, 1. Now, this is going to look funny because you maybe haven't memorized all the bits. In fact, it looks funny to me too because the way it goes. But what we want to do is we want to basically flip those ones, flip, 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 leave the same, leave the same. Watch how we might do that. J exclusive ORed with the complement of 0xff. Oh, what is that all about? This one takes a while to like process, right? If we have a number 0, 0, let's just use 4 hex digits right now, ff, if we take the complement of that, right, all these become what? They're all ones now. What do they all become? Zeros. And the same thing for here, and all the zeros become 1. So that's the complement, right, of that number. And then if we exclusive OR with the numbers, we exclusive OR with 1, right? Anytime there's a 1 in your original, it becomes a 0. And anytime there's a 0, it becomes a 1. So that flips all the other bits. So and then the exclusive OR with zeros means it'll just remain, the same bit will remain. You got to write that one down. I think writing that one down and like working through the binary parts will make sense. Yeah? The complement of a hexadecimal number is 16 minus that number. Yes, you can think of it that way. I don't know that I necessarily would, but yeah. Yeah. Well, not quite, because 15 minus it. Yes, thank you. Yeah. Any other questions on that? All right, let's move on here. Some other things that we can do with our numbers when they're in binary, well, when they're in any form, is that we can shift them. What that means is taking particular bits and moving them either this way or this way inside the number. Okay? If we shift things to the left, we make the number bigger. Okay? Why is that the case? If we say, if we have, what is this? If we have the number, let's say we have 0, 0, 1, 1. Okay. What number is that? Do you remember? 3, right? It's the number 3. That equals 3 in decimal. Okay, if we shift it 1 that way, what that really means is we're going to move all the digits that way. Anything that falls off the end, and we don't care about it. And what we bring in is a 0. So what we would do is we'd shift that this way, and we'd say, okay, fine. The 0 shifts off the end. This 0 goes here. This 1 goes here. This 1 goes here. And we bring in a 0. Now that number is what? Let's see, it's 0 times 2 to the 0 plus 1 times 2 to the 1, which is 2, plus 1 times 2 to the 2, which is 4. So 4 plus 2 is 6. What have we actually done here? We've actually shifted it over by a power of 2, which means we have doubled the number. Turns out if you shift it again, let's shift it one more again, we would get 1, 1, 0, 0. And without even thinking about it, you should be able to figure out what that is. 12. Right? Because we double it. Shifting by 1 to the left means you're doubling the number. Kind of cool. Shifting to the right by 1, you get half the number, although if it's odd, you're not going to get exactly that. You're going to get the floor of that value, as it turns out. Okay, you're going to get the floor of that value. Okay. We have left shifting is actually the easy one. I just showed you that one. Right? If you left shift this number by 2, you shift it over 2 places, okay? And that means that those 2 zeros are going to drop off, the top zeros are going to drop off, and the bottom 2 zeros are going to come in as zeros, and you've just shifted it that way. Does you see how the shift happens in that case? If we shift the bottom number here, 1, 0, 0, 1, 0, 1, 0, 1, by 4, well, these 4 are going to go away. Number's going to start with 0, 1, 0, 1, and the rest is going to be zeros. Pretty good with that? It's not too bad. Okay? Right shifting is actually more interesting, as it turns out. Right shifting works differently depending on the value and the type of number that you're moving. We're going to see this on the lecture that I'm going to do for Monday. You're going to see this in. We have 2 types of shifting. We have what we call a logical right shift, which moves the bits in and replaces them with zeros, just like the left shift did. Okay, so if you're moving a number, if you're shifting like this number 001101111 to the right by 2, and you're doing a logical shift, those two ones go away. The number ends up, the least significant is 101100. That's here, 101100, and then 2 zeros come in. An arithmetic right shift is a little bit different. What it does is it says, what's the most significant bit? That's the one I'm going to shift in. What that means is this. If the most significant digit is a 1, you replace any new ones that you shift in with 1s. If it was a 0, you make them zeros. So 00110111 right shifted by 2 arithmetically gives you these 2 bits shift away, the 1, 1, and then you're left with the rest, 101100, 101100, and then you bring in 2 zeros. But if we have a number like 10110111, the most significant bit is a 1. So when we shift in, we replace anything we shift in with 1s. So that becomes 10110, 1, and then we shift in the 1s because they're 1s. And you're saying to yourself, why would you ever care about that? Aha! It turns out that we use that top bit to tell the sign of our number if we're using signed numbers, and it ends up meaning that we're going to care about that when we talk about signed numbers. Question?
If we did left shift, would it take the least significant digit?
Left shift is only logical. There is no corresponding thing. And it's mainly because we don't care about the bit, like the sign. There's no sign at that end of it. Okay, that's shifting. Okay, all right. C is interesting in that it doesn't precisely define the shift for signed integers. Almost all compilers actually assume that it is arithmetic. And that's because of the fact that we use this certain way of representing numbers, which I'll go over for the lecture on Monday. Okay, more on that coming up. Be very careful when you're using shift operators. It turns out that this, you might think means shift that, add to shifted that. What it turns out meaning is that plus has a higher precedence than the shift, so it actually means that. So you'll do this cool like shifting thing and try to add it to something, and then your numbers will come out all weird, and you go, what's going on? It's because you don't know the precedence rules, right? The precedence rules are really important for those numbers. Okay. That's enough of bits for a minute. Now, all I want to do in the next 7 minutes is introduce you to integer representations. And I'm going to do that by saying, hey, what are some different ways we can represent integers? Okay? All right. We've already mentioned that C has 2 different types of numbers, signed and unsigned. And C is one of the very few languages that has unsigned numbers, as it turns out. Most languages don't bother with them. They just do with signed numbers, but C has them, so we have to think about them. Unsigned means you can't have negatives. Signed means you can have negatives and positives. Okay. We're going to talk about what happens when we use those numbers, when we expand them to fit other types of numbers, and so forth. Before we do that, let's just talk about, let's talk about the ranges, first of all. Okay? The range for some of these, this is similar to what you saw before. The ranges for like the signed character, I mentioned this earlier, is negative 128 to 127. 256 different values, negative 128 to 127. If you don't believe me, count them. Try not to count the long ones. It's going to take you a while. Unsigned long, or longs that are signed, can go from negative 9 something huge all the way up to 9 something huge, right? Integers, signed integers, negative about 2 billion to positive about 2 billion. Okay? The unsigned integers, 0 to about 4 billion, a little more than 4 billion. Those are some of the ranges. Okay? That's what we expect on the myth machines. And it's all based on how many bytes they are, which was in the previous diagram. Okay? All right. What do we do with these numbers once we actually, how are we going to represent them under the hood? We talked about converting decimals to binary, right? We've already thought about that, right? We know that those are our representations for 1, 5, 11, and 15, right? Those are our numbers. Unsigned numbers are actually very nice in that the decimal representation becomes the binary representation just like that. Nothing more to worry about than that, right? You've got a range from 0 to the number of 2 to the number of bits minus 1. Why is it minus 1? Because you got that pesky 0 in there, right? You got 0, so for the integers, or for the chars, for the unsigned chars, you've got 0 up to 255. Can't get that 256, even though that's 2 to the 8th, because 255 is the last one if you start from 0. Count up from 0 to 255, there's your 256 different numbers. Okay. For signed numbers, the question is, how do we represent them? One way is that we could say, let's take the uppermost bit, and we already kind of talked about that, and make it the signed bit. So take a look at what I have here. I've taken my, in this case, 4-bit representation. We're only going to have 4 bits, not 8 or 16 or 32 or whatever. 4-bit representation. And that last bit I'm going to reserve and say if it's 0, it's a positive number. If it's 1, it's a negative number. 0001. 0001 is 1 because it's positive and 001 means 1. Everybody with me there? How about 111? 0111 is 7. If I have 1111, we would say that's negative 7. Why? Because the 1 at the first bit means it's a negative number. Everybody with me there? How many numbers are represented there out of the 16 possibilities that we have with a 4-bit digit number? 14. We've got two other representations that we have to deal with, right? And what can they be, actually? Which number's missing here? Positive and negative 0. We don't like the fact that we might have to deal with positive and negative 0, right? If you have a positive 0 and a negative 0, like that doesn't, like what would that mean? Would 0, 0, 0, 0 be like positive 0 and 1, 0, 0, 0 be, there's no negative 0. Now, I know mathematically you can talk about asymptotes going to negative 0 and positive 0 and all that, but we are not talking about that. We do not like this representation. There's a problem with it. The problem is we can represent 14 numbers very nicely, and the other 2 numbers, the zeros, we only want 1 0. The lecture that I'm doing for Monday, I will explain all of this. I'll see you guys then.